In Lab 4, I examined the motion of a spring mass system where the mass swings from an arc while oscillating on a spring. My goal for this lab is to understand and predict this motion. My results were very good, and I was able to predict the motion accurately. So here is the video of this mass oscillating from the spring. So we have to start out with a fundamental principle, and that principle is Newton's second law, which states that the final velocity equals the initial velocity plus the F net, the overall net force on the object, over the mass times the change in time. So we know the net force equals the force from gravity plus the spring force, and the force of gravity equals negative mg, the mass times gravity, the gravity constant for Earth, and we know that the spring force equals negative k times s. So the spring constant times s, which just equals the spring constant times the length of the spring minus the relaxed length of the spring in the direction of this motion. So how we can find the spring constant is that we look at the period of our experiment, and the period is just the time that it takes to do one whole oscillation. So one of these complete cycle. And as you can see, we have two. We can work with the x or the y values because there's two dimensions to this. So using our experimental data to calculate the time for the period, we can set that equal to 2 pi times the square root of the mass over the spring constant, and we can rearrange that equation to find the spring constant, which equals 4 pi squared times the mass over the period of the period squared. So here are my two different spring constants for x and y. I used in my computation model the 6.88 newtons per meter because it was more accurate, slightly more accurate in the y direction. But so now that we have the spring constant, now we can find the relaxed length, L0. So at equilibrium, the net force equals 0, and this point is right here, and that's where we can calculate this relaxed length of the spring. So we know that the net force equals 0, and so the force of gravity plus the spring force equals 0. So we can set we can plug in those values, and we can set mg equal to the spring constant times s and calculate the relaxed length L0, which I think was 0.14. So now that we know both the relaxed length and the spring constant, we can go back up to our velocity equation and solve for the velocity. And after we know the velocity at each time step, we can plug that in to our position update formula, which states that the final position equals the initial position plus the average velocity times the change in time. So now I would like to run my program, and as you can see, it models the red ball is the experimental, and it's very close to the blue one. And I actually have the picture of the position, the y position versus time for the experimental model, and they're very accurate too. And the last thing I want to talk about is how the energy principle is satisfied. So I created an energy graph that proves that the energy principle is satisfied, because as you can see here, the energy principle states that the total amount of energy transferred equals 0. So the kinetic energy of the mass plus the potential energies of the Earth and the spring all add up to 0. And you can see that by this yellow line that's at 0 the whole time, and then this kinetic is blue, and then the red and green are just the potential energies of the Earth and spring, and this just shows that they all add up to 0 and the energy principle is satisfied. And those are all my results for Lab 4. Thank you for your time.